Blur is easy. Production's subtitle removal is not. A blur hides text by sacrificing picture detail. Removal has to decide exactly what is text, what must remain, and what should replace the hidden pixels. This before and after comes from a real Weydub smart removal task on the same 7-second source clip. The text is gone, but the moving tea, cup, reflections, and camera detail still have to feel continuous. That is why subtitle removal is a video understanding problem, not a rectangle covering trick. Subtitles can change every few seconds, drift with reframing, use different scripts, carry outlines and shadows, or cross faces, clothing, products, and moving backgrounds. A fixed blur band is cheap, but it leaves a visible patch and destroys every useful pixel under that band. A production system needs a selective mask, protection for the rest of the scene, and a plausible reconstruction that survives playback. The goal is a clean source for localization, not a cosmetic way to make the old words unreadable. The first scaling problem is OCR cost. At 30 frames per second, a 100-minute video contains 180,000 frames. Running full OCR on every frame repeats almost the same work, while one subtitle stays on screen for dozens of frames. The workload also grows with resolution, candidate regions, scripts, recognition models, and the number of false detections that must be reconciled. A practical system decodes and samples first, watches for shot or text changes, and spends expensive recognition only when new evidence appears. Tracking and confidence aggregation, then reuse that evidence across the frames between samples. One useful way to reason about that evidence is a temporal candidate graph. This is an explanatory systems model, not a disclosure of Weydub's exact algorithm. Each detection becomes a node. Time, bounding box, script or recognized text, and confidence. Edges connect detections that plausibly belong to the same subtitle across nearby observations. Stable tracks reveal when a subtitle begins, how its position drifts, and where a new phrase or shot should split the track. The system can interpolate masks between OCR samples instead of rediscovering the same glyphs on every frame. The graph also helps reject one-frame noise before it becomes an accidental hole in the picture. Detection is only half the decision, because OCR sees every readable thing. A street sign, product label, app interface, jersey number, or brand mark may be text that the video needs to keep. Removing scene text can change meaning, damage a product, or erase information that was never part of the subtitle layer. Guardrails combine region priors, duration, motion, language hints, text class, confidence, and explicit keep regions. When the evidence is ambiguous, a narrower region or a review checkpoint is safer than aggressive full-frame erasure. A missed subtitle is annoying. A false positive can be destructive. Once the mask is correct, restoration becomes a second problem. Image inpainting uses spatial context around one frame to propose what belongs inside the missing region. A single restored frame can look convincing while neighboring frames choose slightly different textures, edges, or colors. During playback, those independent choices appear as shimmer, swimming edges, or flicker. Video inpainting adds motion and neighboring frames, which can improve temporal consistency, but requires more memory, compute, and scheduling. In general, stable subtitle bands can justify a lighter method, while faces, hands, thin lines, fast motion, and detailed products can justify stronger temporal treatment. No restoration model guarantees the true hidden pixels, so representative review still matters. Now watch the real example again at full speed. In the source, white glyphs and outlines cover pixels near the moving cup and saucer. In the result, the reconstructed lower region stays visually stable, while the pore, bubbles, rim, and reflections continue to move. This is a small, clean example. It demonstrates the output, but it does not imply that every background is equally easy. The same ideas can be organized as an explanatory production systems model. First, decode and sample the video to understand frame rate, motion, subtitle bands, and shot changes. Second, detect text candidates with OCR and computer vision. Third, build temporal tracks so repeated detections become stable objects instead of isolated boxes. Fourth, protect scene text and ambiguous regions from mis-erasure. Fifth, apply a restoration method suited to the mask, motion, detail, cost, and quality target. Sixth, export a clean source for the next localization step. At the documented Weydub boundary, a user uploads video, chooses a removal mode, submits the job, then reviews or downloads the result in Works. A PI or batch can automate delivery around that workflow. They are not quality tiers. Weydub documents 6 removal modes for different scopes and restoration needs. The basic modes are basic full screen, basic region, and basic moving text. The advanced modes are Advanced Lite, Advanced Pro Bounding Box, and Advanced Pro Full Screen. These names describe selectable removal modes, with different input scopes and quality, cost, or availability trade-offs. A PI and batch describe how jobs are delivered or automated. They do not create additional quality tiers. Mode selection is presented here as an explicit product choice, not as an inferred internal routing system. The central trade-off is quality, cost, and speed, not one universally best removal mode. A known subtitle band can often use a more predictable region mask. Unknown or scattered text may require broader detection and more compute. The responsible evaluation is simple. Test representative clips, watch before and after at full speed, pause on difficult frames, and check what the system protected. The useful question is not only, can it erase text? It is, can the system choose the right text, preserve the scene, restore motion consistently, and repeat the workflow at production volume? That full chain is where Weydub fits. Subtitle removal as the first step in a broader media localization workflow.